Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our last lesson of Chapter 7, and this is, one of those lessons that's tucked in the back. It's introducing you to an idea. It is actually related to what we've been doing with association, but it's going to involve categorical variables. And this is a little bit different than using numerical variables, where you take and graph them on a scatter plot, look for your line of best fit, and then decide if there's an association there. This one is going to involve percentages and categorical data. So let's make sure that we're on the same page of what we mean by categorical variables. Categorical variables are variables or data that is non-numerical. So my key example here is when we talk about back in 7th grade, when we were talking about, what were we talking about? Means and medians, and then sometimes we would have to use a mode when we had categorical data, like what's your favorite kind of dessert? And some people say ice cream. Other people might say brownies. Other people might say cookies or pie or cake or whatever. These do not belong on any kind of a number line. This is categorical data, okay? And so what we're going to do is we're going to look at some situations where the independent variable is not a number, but it's like a category. And we're going to show a way that we can represent this information on a bar graph instead of using a scatter plot. Okay, so in previous lessons, you described the association between two numerical variables, such as the amount of fertilizer used and the height of a plant. Some variables, however, such as gender, eye color, names of countries, or weather conditions, are not numerical. Since the data are in categories, non-numerical variables are called categorical variables. Another type of categorical variable occurs when numerical variables are lumped into categories, such as into age groups. So today you will look for relationships in variables that are not numerical. Okay, so here we go. It says the experiments students did with plants in different growing conditions in lesson 7.1.3 caught the attention of a local farmer. He was interested in whether the type of soil made a difference in the height of his corn crop. He planted 2,500 stalks of corn and collected the following data that you see here. You should copy down this table. This type of table is called a frequency table because it shows counts or frequencies in each of the cells of the tables. All right, so while you're copying this down, let me just summarize or just go through. I'm going to read through what it says. Okay, so it looks like you got two different types of soil. You got sandy soil and you've got clay soil. And we're looking to see, of all the 2,500 stalks of corn, by like a certain date, maybe we're talking by the end of the growing season, how tall did the corn get? And so you keep track of all the corn that was planted in the sandy soil, and you can see that 150 stalks were between 0 and 3 feet tall, which is not very tall for corn. Usually they're, what do they say, knee-high by the 4th of July, and then they usually get over 6 feet tall. So 200 stalks were between 3 and 4 feet. 575 stalks were between 4 and 6 feet, and 750 stalks were between 7 and 8 feet. Clay soil, there were fewer stalks that were, or seeds or whatever, that were planted. And so you got 225 of them fall in the 0 to 3 foot range, 150 fall in the 3 to 4 foot range, 200 fall in the 4 to 6 range, and 250 fall in the 7 to 8 range. Now, this is a bit of a problem because they didn't plant the same numbers of stalks in the sandy and the clay soil. So we need to convert this into what we call a relative frequency table, where instead of working with raw numbers, we work with the part over the total, and we convert all of these into percents. And once we've got each one of these as a percent of the total amount of corn planted in sandy soil, and this as a percent of the total amount of corn planted in the clay soil, we'll then be able to compare the data to determine which appears to be the better soil for planting the corn. And so, first thing I would like for you to do, and what CPM wants you to do, is take a look at this data and make a conjecture. That is kind of like give your opinion of which soil would be more effective for growing corn. Okay, based on what you see here, what jumps out at you? What jumped out for me, and if you want to formulate your thought and write it down, you better pause because I'm about to give my big reveal. Okay, so if you just want to hear what I have to say, feel free to just keep playing. Corn planted in sandy soil will grow taller than the clay. I don't know why. I just feel like clay is hard and water doesn't seep down into the roots as easily as it would with sand. So I'm going with that. And while I see some bigger numbers here for the sand, I also have to recognize that there were twice as many plants planted in the sandy soil compared to the clay soil. Okay, so the table of data on corn height used counts because it counted the number of corn stalks. When analyzing categorical data, percents are much easier to analyze. It's kind of like that idea where when you're trying to compare two fractions that don't have the same denominator, it doesn't really work as well. So if we convert them to percents, then they all technically have the denominator of 100, even though we're not writing them in fraction form. But it's understood that out of 100 is what percent means. So that's what we're going to do here. We'll basically convert all of these ratios into percents so that we'll be able to cleanly compare them. So, but first you need to determine the independent variable. So what is it we're trying to figure out here, right? The independent variable is what is affecting the dependent variable. And so what is it that we're testing? What's the variable that we're changing to see how it affects the height? And that would be the type of soil, right? So in this situation, the independent variable is going to be the type of soil that the corn was planted in, because we're trying to see how that soil affects the height of the corn. So what that means is when we set up a table or a graph, a bar graph, we're going to want to have the dependent variable be the height, and the independent variable will be the choices between, oh no, that's going to be, oh, hold on for a second. I'm getting ahead of myself. Let's not go there yet. Okay, so create a second table that contains the data above as percentages instead of counts. So the totals, as you can see here, the totals have to add up to 100%, right? If we add 150 plus 200 plus 575 plus 750, that adds up to 1675. So the percent for corn in this category, plus the percent here, plus the percent here, plus the percent here, all of those have to add up to 100. Sometimes if we round things off a little bit, depending on how the nature of the rounding, it might end up adding up to like 99%, maybe just a touch more than 100, depending on how the rounding goes. But for the most part, it should be very, very close to 100%. So I want to remind you, and this is work I want you to do next. I want you to take these values. So we're going to start with this one right here, which basically we have to remember how the percent proportion works. The part is the 150, and the total, let me actually remind you of the percent proportion from last year. Part over total equals percent out of 100, and our variable here is going to be the percent. We know the part and the total for the sandy soil will always be 1675. So we're going to convert that to a percent by solving for x using proportional reasoning. Now, I would probably recommend just using your calculator. I would recommend you cross multiply every one of these, and you get 150 plus 100 is 15,000 is equal to 1675 times x is 1675x. And then you divide by 1675, so that cancels out, makes that 1x, but you got to take 15,000 divided by 1,675. And let's just go ahead and do that with the calculator. 15,000 divided by 1675 gives you 8.9. I think I would tend to round that up to 9%. Let's call x is equal to 9%. And so there's the reveal. There's our answer. Okay, so I would like for you to pause now and do that for every single one of these sections. And then double check to make sure when you add across that these add up to either 100 or very close to 100 for both the sandy soil and the clay soil. Take your time. This is important, okay? Yeah, this is important. Just do it. There you go. I'll pause and let you get that done. All right. Are you done yet? Have you paused? You need to pause. I want you to take the time to do this. You're going to be going to Del Oro next year. You got to know how to do this kind of math. You got to be willing to pull out your calculator, use the strategies that I've taught you in 7th and 8th grade, and apply them for problem solving. Okay? Oh, they actually showed it right there. I had no idea. I didn't even read down that far. Okay, so if you have not paused yet, please pause because I'm going to start doing the reveal. So it turns out that 200 out of 1675 is about 12%. 575 out of 1675 is about 34%, and 750 out of 1675 is about 45%. For the clay soil, 225 out of 825 is about 27%. 150 out of 825 is about 18%. 200 out of 825 is about 24%, and 250 out of 825 is about 30%. And when we add straight across, this one actually adds up to 99% because of rounding, but this one does add up to 100%. So I feel pretty good about these percentages. I think we should be able to move on to the next step now. So I can actually see right now, I mean, I think I'd be willing to draw my conclusions. While it looks as if the clay soil had like relatively even numbers, right? I mean, 27, 24, 18, and 30. That's not much of a range. That's only a range of 12% between the minimum and the maximum heights that we've got. Well, actually, not heights, but the minimum and maximum percents of these categorical heights here, okay? Whereas the sandy soil had a big chunk. That was like 79%, almost 80% of the corn grown in sandy soil was over 4 feet or between 4 feet and 8 feet tall. So I'm going to say that the data shows sandy soil is better for growing corn. So here's the next direction. It says the farmer is interested in the height of the corn for each of the two soil types. A straightforward way to compare the effect of the independent variable is to make a different bar graph for each independent variable. So that's what we're going to do here. We're going to make one bar graph for the independent variable for sandy soil, and the other one for the independent variable, which is the clay soil. Okay. Our dependent variable is the percent. So we're going to put that on our y-axis. I didn't label the y-axis, did I? There's y, there's x, there's y, there is x. Okay. So copy down our, and this really isn't an x-axis though, but it is kind of an x-axis because this is not a number line. Remember, these are categories. So when they are categories, you're not going like histograms did last year where we had like a true number line along the x-axis and each one of those bars snuggled up to each other. This is going to be a bar graph. So we'll have these as separate categories. Go ahead and label those categories. And let me see what these say to do. It says make a bar graph for the sandy soil. The horizontal axis should be the height categories, and that's what I showed you here. Those are the height categories that we got off the table. The vertical axis will represent the percent of the corn in the sandy soil that grew to that height. Then make a similar bar graph for the other independent variable, the clay soil. Okay. So take some time to create those bar graphs. I'll give you a little hint. There's the 9%. There's the 12% for 3 to 4 feet. You go ahead and do the rest and have all these reference our y-axis number line. Okay. Unpause when you're ready for the big reveal for both bar graphs. All right, how'd you do? Let's take a look at this. We've got our bar graph. So we got the 3 to 5 feet, 9%. 0 to, what did I say? 0 to 3 feet is 9% of the crops. 3 to 4 feet is 12% of the crops. 4 to 6 feet is 34%. And is that 34%? Maybe that's a little bit tall. Move it down a little bit. There we go. And 40. What happened to these? They were perfect before. Hold on for a second. Okay, those are a little bit better. That's a little bit less than halfway, so we'll call that 34%. That's almost exactly halfway. We'll call that 45%. So sandy soil, you can definitely see it trending over to here is definitely a majority of the corn in sandy soil. Now let's look at the clay soil. You got 27, 18, 24, and 30. Notice how in this category, that only is about 54%. Slightly more than 50% of the crops are more than 4 feet tall in the clay soil, while almost 80% in the sandy soil. So I would say that or at least my conjecture was correct. Sandy soil would be better. Is the height of the corn associated with the soil type? Absolutely. We absolutely see that trend. It appears that the corn grows taller in sandy soil. Now, why did you make a bar graph instead of a histogram? Well, because of categorical data. When you've got categorical data, you do not reference it along a number line because your data isn't really numerical. It's categories. Histograms require numerical data. Okay. Okay. One last problem, and then we will be done. The nutrition staff at CPM Diabetic Institute is interested in the impact of 3 new energy bars on blood sugar levels. The staff conducted a study on 1,000 volunteers, okay, and collected the following data. So I think if we add up all those numbers, we would get 1,000. So what we need to do is we need to complete the table by computing row and column totals. What is the independent variable? Okay, so what are we looking to see is having the effect that we're looking for? There, it looks like it says they're interested in the impact of the 3 new energy bars on blood sugar levels. So what effect do these bars have on blood sugar level? Well, that makes the energy bars our independent variable. We're going to see how this affects this. So the blood sugar levels, whether it's lower or higher, that will be our dependent variable, I'm pretty sure. All right, so once again, we're going to create this relative frequency table, which uses percents instead of the raw data, okay? So let's go ahead and see what we can do here. All right, so the direction said complete these tables. Let's get the totals. So how many total mighty bars are there? How many total force bars are there? How many total strength bars are there? Then we will convert that to a relative frequency table by finding out what percent of the mighty bars produced low blood sugar and what percent of the mighty bars created high blood sugar, and so on and so forth. Okay? Go ahead and pause, fill in these tables, fill in the totals, and then do what we did on the previous example and find out the percents for each one of those. And then once we've filled out the percents, then we will create the graph. Okay, so I'm going to go ahead. Let's see if I can do this. You know what? You might just have to pause, go back and forth from here to here, and then copy all that information in. Once you're done copying that information in 10, 15, 20 minutes, however long it takes, then we will do the reveal and we'll see how you did. Okay, let's see what totals we got. 130 plus 120 is 150. 91 plus 409 is 500, and 66 plus 284 is 350. So those are some pretty nice denominators for us to find our percents, right? So if you took 30 out of 150, what percent is that equivalent to? Whoops, that should be out of 100. Shouldn't be too much trouble to see that that is the same as 20%. Is that the same as 20%? 3 out of 15 is the same as 1 out of 5, and 1 out of 5 is in fact 20%. That is correct. Okay, so 20 out of 150. Well, do we even have to do that? We've only got 2, right? So the rest of it has to be 80%. Let me get that out of there too. Boom. All right. So all we have to do is really figure out the first one, and then I don't know what color scheming I'm doing. Hold on a second. All right, got it. I'm OCD. I got to get the right color scheme here. So now if we do 91 out of 500, how much is that out of 100? So once again, you use your proportional reasoning. I think here we just take 91 divided by 5, and what we get as a result is a little bit more than 18%. I rounded it to 18.2%. And then for the last, so that means that the remainder has to be, what is that? What do you add to 18.2 to give you 100? That would be 81.8%. And then for the strength bar, you've got, what was that, 350? And that is 66 out of 350. What would that be out of 100? In this case, I'd probably cross multiply and then divide. Or do you divide this by 3.5? So 66 divided by 3.5 ends up giving you 18, about 18.9. I suppose I could have rounded that up to 19, but I left it at 18.9. And that means that the other one has to be 81.1. So I believe when you add those straight across, no, we're adding straight down, aren't we? We're not going straight across. So when we go straight down, that's 100, that's 100, that's 100. That should work out just fine. So now take that data and put it into the bar graph. So our percents are here on the y-axis, our low and our high. That's I think that's kind of like our dependent variable, right? How does this affect? No, yeah, this is confusing. This is one of the reasons why I'm not really crazy about including this on your chapter test, because it can be confusing. But I would just say this, without even looking at the bar graphs. 80% people that had mighty bars have high blood sugar, and only 20% had low blood sugar. But that's pretty much the same across the board, right? So I don't know that, I mean, are we trying to compare these to see which one is healthier? Because none of them really are doing much for your health. They're all giving you higher blood pressure. But yeah, I think what we can decide is that there is an association between the mighty force, the mighty bar, the force bar, and the strength bar, but they all create higher blood pressure most of the time, at least 80% of the time. So yeah, not quite sure. I think the only thing we can conclude from this is don't eat these energy bars unless you want to get higher blood pressure. So let's take a look at this information here. Yep, there's the 20 and the 80. You can clearly see that each one of those is creating higher blood pressure. And what was the question that was being asked? The nutrition staff at CPM Diabetic Institute is interested in the impact of 3 new energy bars on blood sugar levels. Okay, they absolutely raise blood sugar level. That is the impact. So probably shouldn't eat them unless you're interested in higher blood pressure. All right, so that concludes our lesson, and it concludes all of our lessons for Chapter 7. So we are now going to go into study mode. Why is that there? And start preparing for our chapter test. All right, take care. Bye.
Hey, feeling